Hey there everybody, and welcome to a short video on section 4.4. This section covers a limit rule called L'Hopital's rule, and I know it's spelled L'Hospital's rule, but it's a French guy's name, so it's pronounced L'Hopital. And this is a derivative-based rule that lets us calculate limits from chapter 2 that we were unable to calculate back then. So in chapter 2, there were some limits we came across where we eventually just had to shrug and give up. But now we don't have to give up. We can use this rule based on derivatives to calculate these limits. So the point of this section is to revisit fractional limits from chapter 2 that we couldn't do back then. And it turns out that once you know how to take derivatives, a lot of these limits become approachable. And it's worth pointing out that this rule comes up all the time in Calc 2, L'Hopital's rule. Now, I know that some of you are not going to take Calc 2, and that's fair enough. But for those of you who are, this rule is very important. And for those of you who are not, it's still a nice application of derivatives. So to explain how the rule works, we first need this bit of vocabulary here, indeterminate form. So if you have a fractional limit of this form like this, limit as x approaches a something over something, and a here can be either a real number or, sorry, that's supposed to say or plus or minus infinity. So you can have x approaches 5, x approaches negative infinity, anything like that. If you have a fractional limit like this, it's said to be of indeterminate type 0 over 0 if the top and bottom of the fraction both approach 0. Similarly, a fractional limit like this is said to be indeterminate of type infinity over infinity if the top approaches something infinite and the bottom approaches something infinite of either type, plus or minus. So if the top approaches plus infinity and the bottom approaches negative infinity, that's an infinity over infinity type form. Okay, so let's look at some examples of limits that are indeterminate type and think about what type they are. So here's an example here. Limit as x approaches 0, sine x over x. So as x approaches 0, sine x approaches 0. In particular, sine of 0 is 0. Right? Sine of 0 is 0. So the top approaches 0. And the bottom approaches 0. As x approaches 0, x approaches 0. So this limit has this form, 0 over 0. Indeterminate type, 0 over 0. Here's another example. Limit as x approaches 1, 4 times natural log of x divided by quantity x minus 1. Natural log of 1 is 0. So the top of this fraction here approaches 4 times 0, which is 0. And if you plug in x, 1 for x down in the bottom, you get 0 also. So this is also a 0 over 0 type limit. Okay, this limit here maybe looks like the previous two, but notice if I plug in 1 for x down below, I still get a 0. But if I plug in 1 for x up top, I get 4. So this limit has type 4 over 0, and it's not indeterminate form. Okay, it's not 0 over 0, not infinity over infinity. When I show you L'Hopital's rule here in a second, L'Hopital's rule only works for fractional limits of type 0 over 0 or infinity over infinity. So you cannot use L'Hopital on this limit right here. You have to have 0 over 0 or infinity or over infinity. And we actually know from chapter 2 how to handle this. If you plug in a 1 for x, you get 4 over 0. And so we know this limit doesn't exist. We don't have to learn anything new to say that. Here's another example. Limit as x approaches pi. Okay, so notice sine of pi is 0. Cosine of pi is negative 1. So if you plug in pi for x, you get 0 over 0. So in this section, by the way, it is important that you remember sine and cosine of some basic angles, mainly multiples of 90 degrees. So this is 180 degrees. Sine of 180 degrees is 0. Cosine of 180 degrees is negative 1. So this limit has form 0 over 0. This next limit here with an e to the x in it, if you plug in 0 for x, e to the 0 is 1. Plug in a 0 there, it goes away. So you have 1 minus 1 over 0 squared, which is 0 over 0. This limit looks kind of funny, but let's take it as given. It's a fraction, natural log of x divided by 1 over x. So as x approaches 0 from the right, to think about what natural log does, you have to draw a graph or know what the graph looks like. And so I can't do that in these little slides right here, but you're supposed to know what the graph of natural log looks like. As x approaches 0 from the right, the natural log graph just dive bombs down. So it approaches negative infinity. And as x approaches 0 from the right, 1 over x, you're taking 1 divided by tiny things, like 1 divided by 0.0001, and that gets huge. So 1 divided by something tiny is huge. So this limit has form negative infinity over infinity. And you can omit this negative if you feel like. It's still fine to call it infinity over infinity. You're just communicating that both top and bottom of the fraction are blowing up as x approaches 0. I have to say from the right here, by the way, because natural log doesn't exist to the left of 0. So this limit only makes sense if you're coming in from the right, positive numbers. Okay, that's the idea of indeterminate form. So L'Hopital's rule is a way of calculating fractional limits of type 0 over 0 or infinity over infinity. So like I said earlier, if you have a fractional limit but it's not of that form, don't use L'Hopital's rule on it. L'Hopital's rule is a tool, like the chain rule, the product rule, things like that, and tools can only be used when appropriate. So like you can't use the chain rule to take the derivative of a fraction, for example. Like you would need the quotient rule for that. Now maybe there's a chain rule inside the quotient rule, but whatever. You have to use the appropriate tool at the appropriate time. So all that to say, if you want to use L'Hopital's rule, you got to be dealing with the limit like that. And then what L'Hopital's rule says is this fractional limit f over g actually equals the fractional limit of f prime over g prime. You can just take derivative of top and bottom. And that's kind of neat because back in chapter 3, that's how we thought the quotient rule should work, right? Shouldn't I just be able to prime and be done? And the quotient rule says, no, you can't just do that. But now with L'Hopital, with this sort of limit rule, you can just like take a derivative of top, take a derivative of bottom, and use that limit. And this theorem still works whether you're approaching, say, 6 from the left or the right. Like if that's 6. Don't be thrown off if you see left or right. The law still works. Okay, so I'm going to show you some examples here in a second. And one thing you might be thinking is, well, like, if this limit is difficult, then why would this right limit be any better? In particular, we've seen plenty of examples in class where the original function is not so bad, then you take a derivative and you get something way more complicated. So are we just going to take sort of a tame-looking limit and make it more complicated over here? And the answer is maybe sometimes, but not always. So here's an example. Here's the first limit we thought about, 5 minutes ago. This has form 0 over 0. So this limit equals, and by the way, I put the 0 over the equal sign just to denote that that's the form of the limit, 0 over 0. So this looks like a face looking at you right here. It's not supposed to be a face. It's an equal sign with a 0 over 0 on top of it, just to, again, show the reader that 0 over 0 is the type of the limit. But anyway, once you know the limit has form 0 over 0, L'Hopital's rule says, well, you can take the derivative of sine and put it right here. It's cos. You can take the derivative of x and put it right there. And now you're dealing with the limit as x approaches 0 of cos x. And now you can just plug in 0 for x and it's no problem. Cosine of 0 is 1, so you just get 1 as the answer. So you started with a limit where you plug in 0 for x and everything goes haywire, right? 0 over 0. And if we were back in chapter 2, we would give up. But now we don't have to give up. We take derivative of top and bottom and we get a limit that's much simpler, where in particular we can plug in 0 for x and we get our answer. So this rule is super nice, sometimes anyway. Like in this example, it immediately turned an impossible limit into an easy limit. Right? That's sort of nice. I should also say, by the way, I'm not going to justify to you why this is true. The proof is beyond the scope of the course. So it is kind of a black box, sort of a mystery. But it's a really beautiful result that you can just take derivative of top and bottom when you're dealing with a limit like this. Let's look at a few more examples. So as x approaches 1, 4 natural log of x over x minus 1. That has form 0 over 0 as we saw before. So you are allowed to just take a derivative of top and bottom. Derivative of natural log of x is just 1 over x. And that 4 is just camped out. So you get a 4 over x here. Derivative of x minus 1 is just 1. And now this limit is much friendlier. you can just plug in 1 for x and you're done. You get a 4. Okay, so when you are writing these yourself on your own paper on an exam or something, you do need to write them like this. Anytime you use L'Hopital's rule, you have to justify the use of that because L'Hopital's rule can only be used in certain circumstances, and that's what this 0 over 0 is doing. So on your paper, if you want to write an arrow to that equal sign and then write out, I'm using L'Hopital's rule because the limit has formed 0 over 0. I guess you could do that, but it's much easier just to do this. So it's on the screen here, it gets full credit. As always with limits, you want to make sure you don't have empty limits floating around. You have to take the limit of something. You don't want to write limit as x approaches 1 right here because you're done taking the limit here. So as always, you got to write it this way. Correct, clean, notationally appropriate, and so on. Okay, here's another example. This was 0 over 0 we saw earlier. So you can take derivative of top and bottom. And I realized, sorry, there's supposed to be a negative right here. Typo, I left off the negative. But anyway, you take the derivative of the top, you get cosine. You take the derivative of the bottom, you get negative sign down there. And now, if you try to plug in pi for x, cosine of pi is -1, sine of pi is 0. So you have -1 over 0, and we know those limits don't exist. Like back over here, we didn't know if the limit existed or not. And if it did exist, we didn't know what the number was. But with this, now we can definitively say D and E, and we are done. So that's nice. Okay, here's another example. We already saw this has formed 0 over 0. So if I take derivative of top and bottom, in the top I get e to the x minus 1, in the bottom I get 2x. And now here, notice, if I plug in a 0 for x, I get 1 minus 1 in the top, which is 0. I get 0 in the bottom. So at first glance, it looks like L'Hopital's rule didn't help at all. We started with the mysterious limit right here. We took derivative of top and bottom, and we still have a mysterious limit. Like I still cannot plug in 0 for x right here. So you might want to pause and think about how you would handle this limit right here, this. But one thing you could do is just take this as a fresh problem. Like, what would that be? What if I had just been handed this? Like, suppose I wasn't handed all this over here, right? I wasn't handed this. I was just handed this limit here. How would I handle that? Well, that limit, we just said, has form 0 over 0, so you can use L'Hopital's rule on it. So, in other words, if L'Hopital's rule produces another limit that still has an indeterminate form, you can just do like a double L'Hopital's rule, do it again. And now when we do it again, that sort of works out because we end up with a limit here. I take derivative of e to the x minus 1, I get e to the x. Derivative of 2x is 2. I get a limit where I can plug in 0 for x, and I get my answer of a half. Okay, lastly, this limit here, if you see this in the homework over L'Hopital's rule, you might think, well, I can't use L'Hopital's rule here because L'Hopital's rule applies only to fractions, right? I mean, if we go back, see, fraction, okay? And that is correct, that L'Hopital's rule applies only to fractions. However, you can turn non-fractions into fractions if you want to sometimes, like this. Okay, so check this out. So multiplying by x is actually the same thing as dividing by 1 over x by the rules of fractions. So let me say that one more time. Like multiplying by 2 is the same as dividing by 1/2, for example. So this original limit's not written as a fraction, but you can write it as a fraction if you want to. And then you end up with a limit of form infinity over infinity, as we discussed already. So you can take derivative of top and bottom. So derivative of log is 1 over x. Derivative of, this is x to the minus 1, right? Derivative is negative x to the minus 2, which is this, negative 1 over x squared. And then you can simplify this. It's just fraction division. So this is 1 over x times x squared over negative 1. Like you flip the bottom fraction when you multiply. And when all the dust settles, you just get a negative x out of that because you have negative x squared over x. You get a negative x. And this limit here, you can just plug in 0 for x and you're done. Get 0. So it turns out that this original limit, which was not written as a fraction, if you write it as a fraction, this looks like a mess right here, right? That doesn't look particularly friendly, this log x over 1 over x. But since you wrote it as a fraction with form infinity over infinity, you can use L'Hopital's rule on it. And then as long as you're willing to simplify this fraction, like you're in algebra 2 or something, you can pretty quickly get an answer of 0. So that's how L'Hopital's rule works. It lets you take a fractional limit, and as long as it has kind of a mysterious form that we couldn't handle back in chapter 2, you can take derivative of top and bottom and hopefully get an easier, manageable limit. So the homework is full of extra problems like this. The handout, which is posted to Brightspace, also has tons of extra examples with some solutions worked out. So you can have plenty of practice with this. At some point, showing you more examples is diminishing returns, so I'm going to quit here. But the basic idea is if you're given a fraction or you're given something that you can turn into a fraction and asked to think about the limit, if you try to plug in the value and you get like 0 over 0 or you get infinity over infinity, that's sort of screaming at you to use L'Hopital's rule, take derivatives, and then quit. And again, you can't always do this. So in the homework or on exams, sometimes students will try to use L'Hopital's rule on this fraction. They'll say, oh, okay, so this equals like this. This equals the limit as x approaches 1 of 1 divided by 1 if I take derivatives. You see that? But you can't do that. This is not infinity over infinity. It's not 0 over 0. So you have to be careful when you're calculating limits that you use the appropriate rule. L'Hopital has nothing to say about this, so you can't use L'Hopital on it. Okay, if you have questions or anything, make sure you shoot me an email, and when I get back, I'll be happy to take whatever questions you have. Otherwise, I'll see you when I get back.